So this time around, what are we doing? This time around, we are removing the brick. Okay. This time around, before we remove the brick, the external pressure was equals to this. And since there was a mechanical equilibrium, this would also have been equal to P gas. Correct, right? Okay, cool. So this was before we removed the brick, right? Before we removed the brick. Okay. Now you have removed the brick. What has happened? Right? What has happened, right? The earlier pressure was this. Now you have removed the brick. Right? Now the only thing trying to push the piston down is atmosphere and not the weight of the brick. I'll say it again. The only thing trying to push the piston down is only the atmosphere and not the brick. Okay, so the P external becomes equal to P atmosphere. Okay, cool. This is nice. Okay, let's move forward. Just after removing the brick, the P gas is much more, right? Because the P gas was so strong that it was actually countering the atmosphere and the brick. I'll say it again. The P gas, right, was so strong that it was countering the atmosphere and the brick. Correct. So as soon as you remove the brick, the P gas is like, dude, I'm way stronger than you. I'll push you outside. Okay, so that happens. Okay, cool. And the piston moves up, there is expansion. But during the entire expansion, the P external is constant. It is equal to P atmosphere as we just saw. And so as a result, the volume changes, expansion happens, and your V final essentially is what? More than your V initial, as you can gauge. Take a moment, think about it. Is your V final really more than your V initial? Yes, it is. Think about the V final, V initial, expansion, V initial, final volume. Now, right? How will the graph look? P external is constant. It is equal to P ATM. Even that ugly term is out of the window. mg by A. And the volume has expanded, and as I told you the last time, there should be a sign signifying that the volume is going from the V initial to V final, that is, volume is increasing. In the compression plot, the volume was decreasing, right? This time around, the volume is increasing, right? Okay. Now, this here might seem like a lot of information, so take a minute. This is something that we have already done, not just in today's session, but previously as well. We know that dW is equals to minus P external dV. We know that W is equals to integration of dW, that is integration of P external minus P external dV. Limits are obviously there, V initial, V final. Since this is also an expansion in which the pressure external is constant throughout, this comes out, and the integration of dV turns up into V final minus V initial. Okay. Also, we know that since once the brick has been lifted, during any of these stages of expansion, the pressure is constant and is equals to P atmosphere. Okay, cool. So now when we look at the area under the curve, what does this tell us? This tells us exactly the same piece of information. P external multiplied by delta V, that is the work done by the gas, right? Magnitude, sign, we are intelligent enough, we'll apply, right? Compression has a positive sign, work, expansion has a negative sign. Okay. And then again, the neon green brightening over there is signifying the stage, the work done in a single stage of expansion by the gas. Makes sense? Because, yeah, this becomes dV and this remains constant. So this is your P external. So P external dot dV is the area of this neon green rectangle, right? What is the area over here? P external, which is essentially what? Y multiplied by dV, which is essentially what? X. Length into breadth, height into width, whatever you want to call it, X into Y. Right? Okay, cool. And the point is, you can then again look at it over here. What is happening as it has been removed? Right, we have the plot over there. The each highlight is the each stage and its corresponding work is being highlighted on the plot over there as the stage has been covered.